This lecture describes how to solve the Helmholtz equation in 3 dimensions. We begin with a direct solution of the differential equation. As before, let us first consider that the current density has only a z component. If the x and y components are present, they satisfy the same form of equation, so it is enough to study one component. This is the vector Helmholtz equation for the z component. The corresponding green function problem is obtained by applying the same differential operator to the green function and replacing the source term mu j sub z by a unit point source, delta of r minus r prime. We keep the minus sign on the right-hand side. At first, this form is still a little difficult because the source is located at an arbitrary point, r prime. So we shift the coordinates. We replace r minus r prime by r, which means that we move the source point to the origin. Then the equation becomes a slightly simpler form. Now the point source is at the origin. Because of that, the green function depends only on the distance from the origin and not on the direction. In spherical coordinates, it does not depend on theta or phi. It depends only on r. For a spherically symmetric function, the Laplacian is reduced to the radial form. Therefore, our green function equation becomes an ordinary differential equation in R. Next, we solve this equation for r not equal to 0. Away from the origin, the delta function vanishes, so the right-hand side is 0. To simplify the equation, we introduce a new function psi and write g equals psi over r. Then differentiating gives this equation, and the expression inside the first term is calculated as shown here. Substituting this into the differential equation, we find that psi satisfies this differential equation. This is easy to solve. The general solution is given by this equation, so the green function is obtained by dividing each term by r. The first term represents an outgoing spherical wave, and the second term represents an incoming spherical wave. Since the source is at the origin, we should keep only the outgoing wave. Therefore, g is a exponential of minus jkr over r. The remaining task is to determine the constant a. To do that, we consider the effect of the delta function at the origin. As in the one-dimensional case, we integrate the green function equation over a region that contains the source point. Here we use a volume integral over a spherical region of radius capital R centered at the origin. Integrating the green function equation over this volume, we obtain this equation. The integral of the right-hand side is unity from the property of the delta function. Let us first evaluate the first term on the left-hand side, including the Laplacian. Using the divergence theorem, or Gauss's theorem, the volume integral of the divergence of gradient g is converted into a surface integral over the sphere. The inner product of the gradient of g and the surface element vector is equal to the derivative of g with respect to r. The green function depends only on r, so that the surface integral over the sphere of radius r reduces to the value at r equals r multiplied by the surface area. The result is given by this equation. Next, we evaluate the second term, which involves k squared times g. For a function that depends only on r, the contribution from an infinitesimally thin spherical shell is given by f of r times 4 pi r squared, which is the surface area of a sphere, times dr, which is the thickness of the shell. So the integral over the entire sphere is the integral from 0 to r of f of r times 4 pi r squared dr. The integral can be evaluated by integration by parts, and the result is given by this equation. Therefore, the left-hand side is evaluated as minus 4 pi a, and the constant a is equal to 1 over 4 pi. Hence, the green function is g of r equals exponential of minus jkr over 4 pi r. Now we return to the original coordinates. If the source is at an arbitrary point, r prime, we simply replace r by the distance between r and r prime. Therefore, the general green function is given by this equation. Using this green function, we can write the vector potential A sub 0 as the volume integral of the source J sub z times the green function. If x and y components of the current density are also present, each component of the vector potential can be calculated in the same manner. So we can write the full vector potential in vector form. This gives the general solution of the vector Helmholtz equation. Finally, let us look at one example. Suppose there is a current element of length delta L at the origin, directed along the positive z direction, with current I. In that case, the current density is given by the product of the current moment I delta L and delta of R multiplied by the unit vector in the z direction. This is a very short current source, often called an infinitesimal dipole, or a Hertzian dipole. Then the vector potential has only a z component, and its form is almost the same as the green function itself. We simply obtain mu I delta L times the green function with R prime set to 0. This is the basic solution for a current dipole source in 3 dimensions.